Mathematical modeling of random time walk. References discuss a random time walk, Rtw, model, which can be captured in the following. The Rtw model includes a binary data stream AK that is independent identically distributed data symbols, -1 or 1, a timing offsets tau timing, a channel impulse response HT, an additive Gaussian white noise, AWGN, source and channel output YT. Random time walk model. The Rtw model used for the modeling of timing jitter and performance analysis shown in, can be expressed mathematically as, where t is the bit period, al epsilon plus or -1 are the ni.I.d. And equally likely data symbols, height is the channel impulse response, nt is additive white Gaussian noise, and tau L is the random timing offset for the LTH symbol. This timing offset model can also be expressed as, where tau 0 is the initial timing offset and 0 mean Gaussian random variable with variance sigma tau 02, t is the frequency offset parameter 0 mean Gaussian random variable with variance sigma t2, WL characterizes a random walk and our IID 0 mean Gaussian random variables of variance sigma W2 which determines the severity of the random walk. Kramer-Rao bound, CRB, for timing jitter. The Rtw model described in section 3.1 will be used for the CRLB derivation. To eliminate out-of-band noise at the receiver, the received waveform YT is filtered by a front-end filter with impulse response FT to get the waveform RT, which will be sampled at instant K to get baud rate sample RK given by, where H1T equals height asterisk foot, x equals x0 by 1, xn-1t is the vector of signal component of RK, and in KR0 mean IID normal random variables with variance sigma 2. In this timing jitter models, the random parameters to be estimated are A equals A0 A1, and -1t is the vector of transmitted symbols, and tau equals tau 0 tau 1. Tau n-1t is the vector of timing offsets. For the CRLB computation, the parameter vector theta equals tau ta tt and theta equals tau tat. From section 2.2, U. Represent the total FIM so that the joint estimation is decoupled, and to get the CRLB on timing estimation it is sufficient to evaluate and invert JT tau which is given by, where lambda equals 2 plus c sigma W2 sigma 2t, beta 2 equals beta 1 plus c sigma W2 sigma 2t, and beta 1 equals n2 minus n-1 n2 plus sigma W2 sigma tau O2 plus sigma W2 n2 sigma delta t2, and c equals 2 pi 23 minus 1. The a priori information parameters sigma tau O2 and sigma delta t2 represent the uncertainty of the initial timing offset and frequency offset, being 0 would mean perfect knowledge of these two quantities which is not practical, and the estimation problem is simply that of estimating a random walk. Inverting, 30, to get the CRLB for each tau I leads to, where is the steady state value of the CRLB, and eta equals lambda plus lambda 2 minus 42. The CRLB derived applies to timing recovery systems in general. In practice, timing recovery systems usually involve phase-locked loops. A traditional PLL is typically used for timing recovery, and the receiver employs a timing error detector, TED, to arrive at timing error estimates. For simplicity, a first-order PLL is employed which updates its estimate according to, where alpha is the PLL gain, and epsilon k is the detector estimate of the estimation error. Instead of feeding the TED decisions about the received symbols, if we allow it to have access to the actual transmitted symbols, then we have a trained PLL. The performance of trained PLL gives a heuristic lower bound for the performance of receiver structures that use the PLL for timing recovery. In the steady state CRB and the performance of the trained PLL are plotted for the following system parameters: sigma epsilon t equals 0.5%, block length n equals 500, and the PLL performance being averaged over 1000 trials. As seen in the figure, the performance of the PLL is a strong function of the gain parameter alpha, and therefore it has to be optimized for each SNR. The PLL error variance is plotted for various values of alpha. Taking the minimum of the error variance over all alpha gives us the best performance we can expect using the trained PLL. We see that the trained PLL is about 7 decibels away from the CRB. This gap of 7 decibels has to be put in perspective by the fact that the CRB is not attainable in this case. For the CRB to be attainable, the a posteriori density Fr theta needs to be Gaussian, which is not the case here. Trained PLL and the CRLB.